hypotheses. During the talk, I hope to decide which is true, either because it has a very nice Yale connection, or because according to arXiv, it is your most recent paper. And I will be interested to find out which.
Well, a little bit of both. Yeah, I mean, definitely the Yale connection made me the most excited to get it done before my visit here and actually be able to talk about it here and so on. So anyway, yeah, so yeah, thank you. Thanks for the introduction. Thanks for the invitation. Thank you all for showing up. I know that some of you might have to, jump out in the middle because you have to go teach and stuff like that. I'm aware of that. That's totally fine. I will try to get to at least the main message of the talk within the first half hour so that, those who have to leave will get something out of the talk anyway. Okay, so this talk will be from first principles. I don't expect you to understand anything in the title. The title is the Numeraire E-variable, that's new, and then the reverse information projection. Some of you might know that, but probably not most. So this is joint work with two other professors, Johannes Ruff and Martin Larsson. Again, many of you have probably not heard of them, and the reason is because they're not in statistics and they're not in EE and so on. They're actually in mathematical finance. So it turns out that there are a lot of interesting tools and ideas from mathematical finance that will connect to information theory and statistics in a very fundamental way. And this work it would be absolutely impossible without them. They're amazing, and yeah, so big credit to Johannes and Martin. Okay, so at a super high level, let's see if this will work. No, so it refuses to change my slide. Let's see what. Maybe I have to do it manually. Okay, that's weird. All right, it was working a minute ago, but it isn't anymore. Okay, so at a super high level, this talk is about gambling and betting. It turns out that gambling and betting has fundamental connections to many other areas. So it's connected to online learning. If those of you who know Kova's work on universal portfolios, it's connected to probability. There's actually a game theoretic probability, which is if you want to reinvent probability from scratch, not based on measure theory, but based on games, you can do it. It's connected fundamentally to information theory and fundamentally to statistics. And so this particular talk will only talk about the diagonal, the stuff in red. But I'd be happy, to chat with people afterwards about connections to these other areas and interconnections between all of these and so on. Also, yeah, there is an opening in my schedule sometime in the afternoon due to a recent cancellation. So if anyone is free and would like to chat about any of these things or other things, I would be happy to chat. Okay, so the story is going to start from a paper in 1956 by Kelly, and he was at AT&T Bell Labs, and this was maybe 8 years after Shannon had published his work or had come up with entropy and information theory and so on. Shannon was of course motivated by communication. But Kelly's title of his paper is A New Interpretation of Information Rate. And he says, well, even if you didn't care about communication whatsoever, information theory comes up fundamentally in a completely different sense. So let me just read out the abstract because it's interesting. If the input symbols to a communication channel represent the outcomes of a chance event, on which bets are available at odds consistent with their probabilities, that is fair odds, a gambler can use the knowledge given to him by the received symbols to cause his money to grow exponentially. The maximum exponential rate of growth of the gambler's capital is equal to the rate of transmission of information over the channel, and so on. So he basically connects terms that appear in information theory to the rate of growth of wealth in a gambling game. Okay, so let me try to make that connection a little bit more rigorous. So here's the setting that he considered. Suppose we have IIT coin flips, BI, and they have a known bias P, which is greater than half. So let 0.6, so something of that kind. So the game works as follows. We start with $1 and we can make double or nothing bets. So which means in every round, we bet some fraction lambda of our current wealth on heads. Of course, you'd bet on heads because P is greater than a half. And the coin is tossed. If the coin comes up heads, then you actually earn the amount that you bet. If it comes up tails, you lose the amount that you bet. Okay, so very straightforward betting game. And so he asked the question, what fraction lambda of our wealth should we actually bet at every step? What's the right thing to do? You know the bias, what's the right thing to do? So this is what the wealth looks like. This is the formula for the wealth. After t rounds, it looks like this product of 1 plus lambda times 2b minus 1. 2b minus 1 is just plus 1 or minus 1. So this really looks like 1 plus lambda times 1 plus lambda times 1 minus lambda, things like that. So if you're multiplying your wealth by 1 plus lambda or 1 minus lambda, depending on whether you were right or you were wrong. But that's your wealth after t rounds. And basically what Kelly suggested was you should choose lambda to maximize the expected log wealth in the long run. Okay, so the limit as t goes to infinity of the expected log wealth divided by t. And there's many ways of intuiting why the log wealth, but one reason is if you try to actually maximize the expected wealth, round by round, the actual answer is to bet all your money. Like that's lambda equal to 1 is the right thing to do. In any one round that maximizes the expected wealth. But of course, if you do this many times over and you bet all your money, you're going to go bankrupt very soon. Okay, so it's at some point you'll be wrong, it'll come up tails and you'll go bankrupt. And so he said, well, that's terrible. And it turns out that in this game, you can make your money grow exponentially fast. And what I would like to do is maximize the exponent in your rate of growth of wealth. So look at the log wealth, the expected log wealth, divide that by t. And so that's where he comes up with this, what's now called the Kelly criterion. And if you solve this, you get a bet which is just 2 times p minus half. That's the formula that comes out. Very sensible. If p is actually equal to a half, then it basically says you shouldn't bet. If p is equal to 1, it's heads, then you should bet everything. But if p is 0.6, then you should bet 20% of your wealth on heads. Okay, it's a very sensible strategy. Don't go all in. And then he proves that the optimal wealth, the actual formula for the wealth that you get, looks like the exponential of after t rounds, it's t times the entropy, so the relative entropy of the KL divergence between p and 0.5 plus small o of p. Okay, so essentially your wealth grows exponentially fast with some small term. And so another equivalent way of saying that is this rate of growth of wealth, this expected log wealth divided by t is just actually the relative entropy. Okay, so in this case, I don't need to take the limits and so on because it's really an IID game that's repeating round by round. And so it's really the one round thing that really matters. And so in each round, you can just calculate that the expected value of log this is just the KL divergence. And so he says, so it turns out that in this betting game, I didn't want to communicate, I didn't want to do anything else. I just want to play a betting game. Well, turns out that the optimal way to play that betting game is fundamentally connected to the KL divergence. Okay, so he writes this paper 8 years after Shannon.
So, what's the objective? Is it
expected value of log wealth divided by t. He wants to choose lambda to maximize this because your wealth will grow exponentially fast, as you can see. With this lambda star choice, your wealth can grow exponentially fast. So he says there is a way to bet so that you start off with $1 and your wealth grows exponentially fast. You should try to maximize that exponent. How fast can it grow? And he says, well, if you take the log of the wealth, then the exponent comes down. And you take the expected value, that's really getting at the exponent. So this is saying I want to maximize the exponent. And so he says, well, the best possible exponent that you get is the KL divergence. That's the best possible exponent. Okay, and so the optimal gambling strategy is related to the best possible exponent.
So the expectation of this over t doesn't depend on t?
Yeah, it does. Of course not. Yeah, it doesn't depend on t because the optimal wealth after t steps is exponential in t times the KL divergence. So when you take log of the wealth and you divide by t, you only have that term left, right? So
I'm just trying to understand why is this optimization problem interesting?
Any other choice of B makes a smaller exponential growth of wealth.
No, but I can forget about the limit. So there's
yeah, that's right. Yeah. I've just written it as a limit.
It refers to the more general context.
That's right. Yeah. Right. So it's like in this case, it's the one round game. It's just expected value of log 1. It's right. But if I now you can ask the question which people did ask afterwards. If I don't know the bias of the coin P, then what's the optimal strategy and can I achieve it and so on. And so it'll turn out that there's something called Khrushchevsky-Trofimov, which is it's like a universal coding strategy, like a mixture strategy that achieves an oracle rate of growth of wealth. That is, imagine that, God knows P and God can play, this particular Kelly bet strategy. I don't know P, I play the Khrushchevsky-Trofimov strategy. My expected log wealth divided by T will approach the oracle in the limit. So things like that. But of course, as I said, for this particular game, it's just really a one-round analysis. Yeah. Okay, so soon after that, most people probably know Breiman, but they know Breiman for things like bagging and random forests and stuff like that. But in the 1960s, Breiman actually wrote a paper on gambling, and his title was Optimal Gambling Strategies for Favorable Games. Again, I'll read the abstract because it's super interesting. People don't write like this anymore, but he says, assume we are hardened and unscrupulous types with an infinitely wealthy friend. We induce him to match any bet we wish to make on the event that a coin biased in our favor will turn up heads. And he describes. So it's a very nice way of writing. I like it. But anyway, what he really does in his paper is he generalizes Kelly betting to other settings. And in particular, he proves that, well, there's Kelly criterion, which is this expected log wealth, but you might have other criteria, which is if you have a threshold wealth and you want to minimize the expected time to reach that threshold wealth, or if you have a threshold time and you want to maximize your expected wealth at that threshold time, then at least he shows that asymptotically, as these thresholds move to infinity, Kelly betting achieves exactly like optimizing the Kelly criterion also optimizes these other criteria. So some nice results in Breiman's paper and so on. So that's kind of historically what happened. Now, this is all again in information theory, but I want to make clear what the connection is to statistics. So there's this way of thinking about hypothesis testing as effectively betting. Okay, so it's testing by betting. This was pioneered by Wolf and Schaefer in a couple of textbooks on game theoretic probability. But this is the idea. So if you want to test a hypothesis, you set up a game that has two properties. It's a game of chance. It's a betting game. And the two properties are, if the null hypothesis is true, then there's no strategy that can systematically make money. And if the null hypothesis is false, then a good betting strategy can systematically make money. Okay, so I'm going to set up a game with these two properties. And then in that game, wealth in that game is directly a measure of evidence against the null. If you have a large wealth, there's more evidence against the null. Because if the null is true, you shouldn't be allowed to make money. So if you've made a lot of money, the null is likely false. And so in that case, every strategy of the statistician corresponds to a different estimator or test statistic. So there are good and bad strategies for betting, just like there are good and bad estimators or test statistics. And so this basically changes the problem of hypothesis testing, like we are familiar with in statistics, to or estimation, which is a dual problem, to basically one of game and strategy design. You give me a hypothesis test, I translate it into a game, and I design a strategy to play that game well. And then I can design optimal, interesting tests and so on from it. So that's and so you should think about Kelly's game as basically the null hypothesis is that it's a fair coin, and the alternative hypothesis is it's a coin of bias P. Okay, so he did not write anything about testing. He didn't write it in that language, but if you translate it to that language, that's basically what's going on. Like I'll generalize it a little further, so maybe it's more transparent what the game is. So let's say we have a point null and a point alternative. Okay, so like let's say that we are testing that our data is coming from P, and the alternative is that our data is coming from Q. Okay, and so right now we'll assume that P and Q are absolutely continuous with respect to each other. So you said, okay, this is a standard hypothesis testing problem. So what's the game? Where's the game in this? Okay, so or like suppose you have many data points. Sorry, x1, x2, and so on. That IID. So what's the game? So the game is going to work like this. I have some initial capital, which is 1. Like I start off with $1. And in each round, first, the statistician declares a bet. A bet, in this case, is determined, it's called ST, is the bet in round T. It's just a mapping from the outcome space to 0 to infinity. And the bet has to satisfy this condition, that is, if the null is true, the expected value of ST of x given the past is less than equal to 1. If the data is IID, I don't have to condition on the past, but this is more generally what you would have to do. So this is what you mean by a fair bet, which means under P, the expected value is less than equal to 1. And then reality actually reveals XT, you see the outcome. And then your wealth gets multiplied by this ST of XT. That's your realized wealth. So ST of XT is the multiplier of your wealth. And the constraint is saying that if the null is true, you should not be able to multiply your wealth by something more than 1. So it's like the multiplier of your wealth is at most 1. So I'm taking a product of things that are are at most 1. So your wealth is a non-negative super martingale, or I don't want to use those terms, but hopefully this is clear that what this game is trying to do is saying if the null is true, you start off with $1, and in expectation you're multiplying by something less than 1. So you shouldn't be able to make money in this game. Okay, so that's the game. The constraint is really on the null. So what is a good betting strategy? It's one, like I said, we're going to talk about, for example, log optimality. What you want is that under the alternative Q, your wealth grows really fast. That's what you would like, is that if the null is true, there's nothing I can do. But if the alternative is true, I want my wealth to grow really fast. So what is the log optimal betting strategy? The answer is just likelihood ratios. Okay, so this is like an analog of the Neyman-Pearson lemma to the betting scenario. So the log optimal bet and the teeth round is just Q of X by P of X. That's a function. It's a non-negative function from X to 0 to infinity. It's non-negative. And under P, it has expected value at most 1. Okay, so it's a valid bet, but it turns out it's also the optimal bet. And so the optimal wealth process here says, what is your actual wealth? It's just the likelihood ratio process, right? So this is very intuitive and very natural.
Yeah,
Yes.
I have fun with the terminology here. So we call it likelihood ratio and probably in statistics, but for a gambler, maybe we should call it a livelihood ratio.
That's a good point. Yeah, well, yeah, that is true. This is how they make their livelihood. So it is maybe I should have that typo in one of my papers by mistake. I'll credit it to you. Yeah, okay, so anyway, so the livelihood ratio process is actually the optimal wealth process in this case, very intuitive. You can notice that it is a positive, it's strictly positive in this case. It's a positive martingale under P, which means that no matter when I stop, the optional stopping theorem says no matter how I stop, the expected value of my wealth is at most 1 if the null is true. Okay, or if you take logs and apply Jensen's, then the expected value of my log wealth is less than 0 if my null is true. But under the alternative, if the data is coming from Q, then this grows exponentially fast. And the expected value under Q of my log wealth is actually positive. And what does it equal? It equals the relative entropy. That's the definition of relative entropy. If it's the expected value of Q of the log of the likelihood ratio, that's just the relative entropy. And so essentially, again, in this case, we're seeing, like Kelly saw, but maybe in slightly more general notation and setup, that the optimal betting strategy yields a wealth process whose exponent is given by the relative entropy of Q and P. Okay, so this is the more general story. Okay, so to summarize what was known, for testing a point null against a point alternative, likelihood ratios are optimal per round bets. The optimal wealth is the likelihood ratio process. The optimal rate of growth of wealth, or the exponent of the wealth, is exactly the KL divergence or relative entropy of Q to P. So this was known. So now the question I'm going to ask is, what about composite nulls? Okay, so I have the story is very simple for point nulls. What about composite nulls? So significant progress was made on this by Peter Grunwald and co-authors in 2 papers, Safe Testing, which is published in JRSSB as a discussion paper, and an archive paper, which is Universal Reverse Inference Projection and Optimal E-Statistics. But in our work, we complete the story. So essentially, what I'm going to tell you now is a complete story about composite nulls. Okay, and it's a very clean and simple story about how do we test a composite null, or how do we gamble against a composite null.
A quick question. So why only composite null, not composite alternative?
I'll get to that at the end, but it turns out that to deal with composite alternatives, there's kind of only one way forward. It's actually mixtures. So essentially, averages of martingales are martingales, averages of bets are bets. So it turns out that if you can find out the right thing to do against a particular alternative, and instead you have a set of alternatives, then the right thing to do is to define a mixture over that alternatives. And so it'll be a derivative of this theory. So the difficulty is actually in handling composite nulls, and then composite alternatives will be handled much more easily. But I'll get to that at the end. We just have to go step by step. But it turns out that if I had first generalized it to composite alternatives, the answer is very simple. But if I generalize to composite nulls, the answer is very non-trivial. So how do I bet against a composite null is very non-trivial. Okay, so let me summarize what our setting is. We have a composite null hypothesis script P. So script P is going to be a set of distributions, and we have a point alternative Q. Okay, so the data is either drawn from some P in script P, which we say the null is true, or it's drawn from Q, in which we say the alternative is true or the null is false. Okay, now a valid bet is an E variable. Okay, so this is a one round bet. So earlier I told you about the sequential setup and so on. In each round, I have to come up with a bet. So everything in my talk is going to be about, it's just one round, what's the right thing to do? Okay, so a valid bet is an E variable, which, as we said before, is a positive, a non-negative random variable, X, such that the expected value of X is less than equal to 1 for every P in script P. So you should think about X as being the multiplier of your wealth in each round of the game. And this constraint is saying no matter what null is true, I should not be able to multiply by my wealth by more than 1. Okay, and so that's the constraint. So that's called an E variable. And so the question is, what is the optimal one round bet X star? Okay, and earlier it was the likelihood ratio if P was a point null, but now we have a composite null. What's the optimal one round bet? Is it unique, and can we characterize or derive it? That's the question. And here's the answer, because I know some people have to leave. It is the likelihood ratio of Q to a very special element P star, which we will call the reverse information projection. So this P star, and I'll tell you why that name and so on later, but the optimal bet is the likelihood ratio of Q to P star. And the key about all of this is that it is under absolutely no assumptions on script P and Q. That's what makes this paper interesting, or this talk interesting, is that I am not going to assume there's a reference measure, that there are densities, that script P is convex, nothing. There's absolutely no assumptions on script P and Q. There's just arbitrary sets of distributions and some alternative distribution. And the answer is always a likelihood ratio of Q to a very special element P star, because that's yeah.
So P star would be very close to one of those entries or not? One of those P.
Usually not. Typically not. And I'll get to that. Yeah, usually it's not, but sometimes it is, and we'll see examples of both soon. So our work basically tells a complete story about this pair X star P star. So X star and P star are actually dual pairs. X star is an E variable. P star is X star is a bet, and P star is a distribution in quotes. It's a positive measure. And they're dual pairs in a very strong sense, and we will tell a complete story about X star and P star. So if you don't like hypothesis testing and can't think about composite nulls and so on, here's the setting rephrased in terms of betting. You say, I don't like statistics, I just want to bet well, that's fine. This is the story in terms of betting. So let omega be a set of possible outcomes. There's a forecaster that claims that script P describes the world well, which means that outcomes or events are well described by some probability distribution in script P. There's a skeptic that thinks that the forecaster is bogus and they're inaccurate, but the skeptic thinks Q is a much better model for the world. Okay, the forecaster offers bets based on his forecasts. Okay, so a valid bet in this case, the forecaster says, since I think that script P is a good model for the world, you can bet against me and you can make money if I'm wrong, but a valid bet is something which, if I'm actually right, you shouldn't be able to make money. So if script P is actually true, then the expected value of your payoff is actually less than equal to 1. And so forecaster offers these bets, and then skeptic has to just pick a particular bet. So skeptic says, okay, I'm picking a particular bet X. Then we observe the actual outcome, and skeptic's realized payoff is X of omega. That's the realized payoff. And the question is, which bet should the skeptic pick? How should the skeptic play this betting game? And the answer is the log optimal bet X star is the likelihood ratio of Q to the reverse information projection P star. That's the optimal thing. So this is just, I'm just removing all the testing from it and saying it as a betting game, just to make it clear.
Can I just have one question about notation? So
Yeah.
you're describing X as a random variable.
It
I'm
is.
thinking of it as a function.
It's a random function. Yeah, it's a
Or
random
it's,
function.
or it's a function that
Yeah.
then becomes random once we sample its input according to P.
Yeah,
Okay.
or Q. Yeah,
Or
exactly.
Q,
Yeah, it's
right,
random. function.
okay.
Yeah, that's right. Yeah.
So eventually, there will be some kind of absolute probability here.
That's the whole point of my work, is to say no. We do not need any absolute continuity.
No, between Q and P star.
No. Oh yeah, between Q and P star, yes.
Oh.
So it'll turn out yes, but not between Q and script P. So script P is a set of measures.
Yeah.
But P star, yes, it'll turn out that P star is related to Q in a fundamental way. Yeah. Okay, so at this point, at least, if people have to leave to teach or something like that, they know the answer, that the right way to bet is related to this reverse information projection and so on. And but now I'll actually get into the details. So the next two slides are going to be, here's the optimal bet on E variable and here's the optimal P star. So what's this dual pair? Okay, so first we're going to define something called the numeraire E variable. The term numeraire comes from finance, and I'm not going to tell you the real reason it comes up, but we call it the numeraire E variable. So here's a first theorem. Under no assumptions on script P and Q, there's always a special E variable X star, which satisfies two properties. First, it's an E variable, which means it's non-negative and its expected value is less than or equal to 1 under the null. Second, for any other E variable X, we have that the expected ratio of X to X star under Q is less than or equal to 1. Okay, we call this the numeraire property. So remember that under Q, we want X star to be large as possible. This is one way of saying as large as possible, right? So if you take any other bet you could have made, X divided by X star is less than or equal to 1 in expectation under Q. Okay, that's what we call the numeraire property. So this X star always exists. It is unique up to Q null sets. There is a unique optimal bet to make. And in fact, this X star is the numeraire if and only if it's log optimal. So like log optimality and the numeraire condition are very closely related. So if you apply Jensen's inequality again, you get two interesting other statements. So for example, if you apply Jensen's inequality to the function 1 over X, you get that the expected value of X star divided by X is greater than or equal to 1. So again, there's another way of saying, well, X star is better than X under Q, but it's a consequence of Jensen. And if you apply Jensen's with log, you get that for any other X, the expected value of log of X by X star is less than or equal to 0. Okay, so this is log optimality. But the reason we define things our way and not via log and things like that is it turns out that the expected value of log X or X star could actually be infinite, in which case you'd be writing infinity less than or equal to infinity and you're not sure what's going on. This avoids all of those problems. It turns out that when you write it this way, it's well defined, it's unique, it always exists, no measure theory weirdness going on. It's just unique and always exists, right? So it's very clean. So that's X star. Now I'm going to introduce P star to you. I'm going to define P star for you. And I'm going to define the measure P star by defining its likelihood ratio or Radon-Nikodym derivative with respect to Q. Okay, so I define it, I say define P star as dP star by dQ. The likelihood ratio with respect to Q is 1 over X star. Okay, I define it that way. So this is it gives rise, so X star is uniquely defined. This measure P star is uniquely defined. Okay, it comes from this definition. So if X star is actually infinity, which can happen in some cases, then then this is understood to just be 0. And by definition, P star is actually absolutely continuous with respect to Q because we define its Radon-Nikodym derivative in this way. It's by definition absolutely continuous. And also, if you invert things, then again by definition, X star is just dQ by dP star, and the optimal bet is this likelihood ratio of Q to P star again. Okay, so right now, there's no reason I should be calling P star the reverse information projection. P star is just a positive measure that I define in this way. Okay, in general, it's not a probability measure. It's a sub-probability measure, meaning that it actually integrates to something less than 1. Could be a probability measure, but in general, it's not. And P star, it turns out, lies in a very fundamental object, which I have not seen much in the statistics literature or ever in the statistics literature, but I would love to know of references. There's a very fundamental object called the bipolar of your null hypothesis, script P, which I'm going to define as follows. It's convex geometry. So the way to think about things in terms of convex geometry is that integrals are dot products. And so that's what's going on here. So the polar of P is non-negative random variables such that the dot product between X and P is less than or equal to 1 for all P. That's actually just a set of E variables. So the set of E variables is a dual object to the set of distributions. It's the polar, actually. That's the definition of the polar. And then now, if I give you the polar, you can define the bipolar. And the bipolar of P is the set of all positive measures such that the expected value of X is less than or equal to 1 for all E variables. So you go from the set of distributions to the set of all E variables back to the set of all distributions. Distributions in quotes because now they're not normalized to they could integrate to something less than 1. And the bipolar is what we call the effective null hypothesis. That's actually the problems which are not, you cannot test against the bipolar. I don't want to get into that right now, but turns out that the bipolar is the fundamental object for hypothesis testing. And in this case, you have no power against the bipolar, but P star lies in the bipolar. So if you're asking where is this, I've defined this funny measure P star, where does it lie? It lies in the bipolar of P. And I will come later on to tell you a little bit more about the bipolar, but for now, let's just say P star lies in the bipolar of P. That's what we know.
Last question.
Yeah.
So what I'm doing over here is we are extending P to a larger class.
Yeah.
And is there any, this kind of definition is kind of interesting. Is there any more direct way,
I will tell you. Yeah, I'll
so
get.
that, computation more easy,
I'll get to it. Yes, all of these are good questions, and yes, I will get to it soon. Yeah. Okay, so just for simplicity for the rest of this talk, in the paper we don't need it, but for the rest of the talk, I will assume that Q is absolutely continuous with respect to script P, which is a very, very weak assumption. Okay, and it's important to understand what that assumption says. What this says is that whenever P of A equals 0 for every P, we also have Q of A equals 0. It's a very weak assumption, which means that there's no event which is impossible under the null and possible under the alternative. The reason why it's only a simplifying assumption, it's not a real assumption, is because if there's such an event, if there's an event which is impossible under the null and possible under the alternative, you can set your bet to be infinity on that set, because essentially it's impossible under the null. So you can define it to be whatever you want on that set, and so you can make infinite money. If that event happens, you can immediately reject the null, and you have infinite wealth. And so somehow this is,
if I'm a governor, I will allow that, right?
of course. So, but what I'm saying is, in the paper, we make this, we explicitly show how to handle the case when Q is not absolutely continuous with script P. We do that, but for the talk, just to avoid this kind of trivial, it's a trivial case because I just get infinity for free on some set, and to avoid that, I can kind of remove it, and I can just condition on not being in such a set. So it's a very, very small assumption. It does not imply a reference measure. It does not imply densities. It does not imply, it's super weak. It does not imply that Q is absolutely continuous with respect to a particular element of P. It just says that if everybody in P thinks an event is impossible, then Q also thinks it's impossible. It's really very weak, but that just will simplify some of my statements. Okay, and then the actual definition of KL divergence, I'll define it in two ways. So this is the more familiar way, is the expectation under Q of log of dq by dp. If Q and P are absolutely continuous, it's infinity otherwise. But there's another way to write it, which is often more convenient in our case. Let P superscript A denote the absolutely continuous part of P with respect to Q. Then you can also write the KL divergence as the expected value under Q of minus log of dpa by dq. Okay, so I've just flipped it, but now you have the absolutely continuous part. Anyway, so I hope if people don't know this, this is just true and not so hard to prove. Okay, so here is so that was just notation. Okay, so this is a strong duality statement. I've just assumed that Q is absolutely continuous with the script P for simplicity. The paper has a more general strong duality statement. So let X star be the numeraire that we know it exists and it's unique and so on. And let P star be some element of the bipolar that is equivalent to Q. Okay, equivalent to Q means that it's absolutely continuous with respect to Q, and Q is absolutely continuous with respect to it. Okay, so then the following three statements are actually equivalent. First, the statement is P star is the reverse information projection, meaning it's actually defined by dp star by dq is 1 over x star. It's that. The second statement is that if I look at the expected value under Q of dpa by dp star, it's actually less than equal to 1 for all P in the bipolar. And if I look at the expected value of under Q of log of dpa by dp star, it's less than equal to 0 for all P. So again, for people who are familiar with information theory, some of these things might make more sense. This is called the description gain. So if your data is coming from Q and you describe it with, with respect to P star, then changing it to some other P cannot gain you anything in terms of description length. So somehow that's what this is saying. P star is special in the sense of you cannot gain anything by shifting to another P when the data is coming from Q. Okay. But anyway, these are equivalent to P star being the reverse information projection. And if any of these hold, which means it's like, yeah, then one has a very beautiful and simple strong duality statement, which is that the expected value under Q of log X star, which is what we were interested in, equals the supremum over all X in the polar, which are all possible E variables of the expected value of log X, which equals the infimum over P in the bipolar of H of QP, which equals H of QP star. So X star and P star achieve this particular strong duality, maximizing the growth rate of E variables equals minimizing the relative entropy with respect to things in the bipolar. And they're achieved by X star and P star, where these quantities may equal infinity. So if any of these quantities is plus infinity, then all of them are plus infinity. That's actually fine. So we'll see examples of this kind where things are just seem to be, it seems like you can't even get started because you don't, how do you define KL when you have discrete and continuous distributions and so on? Turns out to be no problem. You can find the reverse information projection, you can find the numeraire, and strong duality holds. Okay, so that's one of the major results in the paper. Under no conditions whatsoever, this strong duality always holds. Any questions about it?
You're going to relate this to earlier work.
Yes, that's my next slide. Yes.
Is there a way to formulate it where the minimization is in the first argument?
Yeah, that's called the information projection, but that actually, yes, but I'm not going to do it here. Like it corresponds to a different utility function, which is not log and so on. So if you move to other utilities other than log, then you get other things. And I'll get to that. My last slide is actually about going beyond the log utility function. Okay, so the name reverse information projection really comes from this latter equality, right? So this P star is something that appears to minimize the KL divergence among all elements in the bipolar of Q to P. So that's where the term reverse information projection comes up. So information projection is when you minimize with respect to the first argument. Reverse information projection corresponds to minimizing the second argument. And so that's where the term comes from. This is what justifies us in calling P star the reverse information projection. Otherwise, it was just a positive, like it's just a positive measure that a sub-probability measure that I had defined, in some way. But it turns out that this is why it is the ripple. Yeah, so this is where we go back to, if you read my abstract, an amazing PhD thesis by Jonathan Lee. It's amazing because 25 years after it's published, we are still going back to it and reading its proofs and its conditions. And this is, I don't know, quite rare for a dissertation to have such a long-lasting effect. But so this was called estimation of mixture models under Andrew. And so he defines a new information projection theory, a warning that his Q and P are flipped with respect to mine. But here he says, well, I've tried to minimize the KL divergence. But he defines the information projection in a different way. It says, given a probability measure P with a density, so it requires densities, and a convex set C of densities. So again, it needs to be convex and have densities. A special function Q star is called the reverse information projection if for every Qn such that dpqn converges to this infimum dpc, we also have log qn converging to log q star in L1. Okay, so it seems like it's an abstract definition, but it's like basically like the infimum may not be achieved by a distribution in your set. And so if you have a sequence that converges to it, then you also, if you have log qn converging in L1, then that's called the so and so then he proves some properties about it, that firstly it's if you have a convex set of measures with densities and so on, then it exists and it's unique, and dpq star actually achieves this infimum. The infimum is achieved with equality, and then you have this integral of pq by q star is less than or equal to 1 and so on. So what you should view our work is it recovers this as a special case because we have no assumptions. We don't need densities. We don't need a convex set. We don't need reference measure. Nothing of that.
What'd you call it? The P00?
Yeah, the bipolar. Right.
Bipolar.
Yes.
It's a convex.
That's a convex set. Absolutely. That's right.
Can you comment then on the relationship between just allowing any convex set versus the bipolar?
Yeah, it has to be the bipolar. So P star always lies in the bipolar. So maybe I'll back off a little bit. So our definition of reverse information projection is a more general definition because you can define it always. coincides with this definition if you put it in this setting where you have densities in a convex set. It's exactly the same definition.
So Bell and Clover assumed that there's a Q star in C.
Yeah.
Here we generalize that a little bit. Are you saying that this Q star will be in the bipolar?
Yes, that's exactly where it will be.
Okay.
Yeah, it is the same definition as I said. So this Q star will be in the bipolar, and yeah, there's no, in some sense, there's no way around it. Yeah.
Is the bipolar more than the convex?
I'll get to that soon. In 2 slides, I will get to that. Yeah, that's a great question, and yes, it's larger than the convex hull.
Depends on how you take limits. when you take
Exactly.
bipolar.
Exactly. It's just about when you don't have. Yeah, let me get to it in a couple of slides. So it's yeah. Okay, and then there's this very recent work by Peter Grunwald, Peter Harmos, and Tyron Lardy on arXiv. It's probably in submission at a journal, in which they say they actually generalize the reverse information projection using something called description gain. And so they say that P denoter, you have a finite measure and a set of measures, and then they all have densities with respect to a common sigma finite measure. So there is a reference measure. Then they assume that the set is sigma convex, which is closed under countable mixtures. And they assume that there is at least one Q star such that P is absolutely conditional to Q star. So like all of these assumptions can be avoided. So it turns out that they generalize Jonathan Lee's work to, a little bit by relaxing some of the assumptions, but we can remove all the assumptions. You actually need absolutely no assumptions for X star and P star to exist and be unique and so on. So it avoids all assumptions. Okay, so yeah, people have been asking about the bipolar. So this is a little bit more about the bipolar. So script P, just imagine it to be some set of distributions. I've just drawn it as a star here. Then the bipolar of P is this shaded gray region. Okay, and in general, it contains sub-distributions also. It contains distributions also sub-distributions. And P star lies in this bipolar. And Q is outside this set. And typically, if Q is inside the set, the testing problem is trivial. You have no power against anything in the bipolar. But if Q is outside that set, then that's the relative entropy that we've been talking about, the relative entropy of Q to P star. Okay, so let M1 denote the set of all probability measures, and M plus denote the set of all non-negative measures. So just in terms of a term, this term comes from topology, but a set C is called, a set of positive, non-negative measures is called solid if for every P, P prime is also in the set when P prime is less than equal to P. Okay, so it's, yeah. So since we allow for sub-probability measures, so if a measure is in the set, then everything smaller than it is also in the set. That's what we mean by solid. Okay, so here's 2 facts. So if script P is finite, then the bipolar is actually just the convex hull of P. Actually, the intersection with M1 is on the other side. The bipolar of P intersection M1 is just the convex hull of P. Okay, so they're actually the same thing when P is finite. Here's another case where we can kind of relate it, but if there is a reference measure mu, that is everything has densities with respect to mu, then the bipolar is everything in the bipolar also has densities with respect to mu. Okay, so if your original P has densities with respect to mu, then the bipolar also has densities with respect to mu, and it is the smallest mu closed solid convex set that contains P. Okay, that's a mouthful, but anyway, so there's a particular way of defining closure with respect to mu. It's in probability with respect to mu, and then there's solid, which I've defined, it's convex, and then it's the smallest mu closed solid convex set that contains P. Okay, so intuitively, the real difference for testing, the real difference comes up when you don't have reference measures. When you have reference measures, the convex hull of P is the right object to look at. Okay, and so Kraft's theorem, if you've heard of Lecam's theorem or Kraft's theorem and so on, it'll tell you that if your distribution is outside the convex set, you can test and things of that kind. So it's the right object when you have a reference measure. But if you've seen the proof of Kraft's theorem, if you've seen the proof of Lecam's theorem, if you want to look, so Kraft actually, it's called Kraft's theorem, but Kraft cites Lecam in the paper, says this proof is because of Lecam. So you can call it Lecam's lemma or Kraft's theorem. If you look at its proof, it's based on the Hahn-Banach theorem. The Hahn-Banach theorem is a separating hyperplane theorem in L1, L infinity, and it needs a reference measure. There's just no way around it. You need a reference measure for that Hahn-Banach theorem. And so like all of the stuff that we typically do is based on convex hulls, but they assume a reference measure. If you don't have a reference measure, convex hull is not the right object, bipolar is the right object. Okay, so that's something I'm formalizing in follow-up work. Okay, so a little bit more about this pair X star and P star. So recall that X star is actually dq by dp star by definition of P star. We define it that way. And we say that P dominates P prime if P of A is greater than P prime of A for all A, and it's strict inequality for some A. So in that case, we say that P dominates P prime. That's just some notation again. So here's an interesting theorem. Okay, again, let Q be absolutely continuous with respect to script P to keep things simple. There's a more general version in the paper. So let X star be some E variable, okay, and let P star be defined by dp star by dq is 1 over X star. So we have some E variable and we have some measure P star. Okay, then X star is the numeraire if and only if P star is in the bipolar. Okay, so if you have a guess for the optimal E variable, you just have to check is P star in the bipolar, and you know it's the optimal E variable, this numeraire. So it's like it's an interesting if and only if. And if this is true, so in this case, we know that X star is actually not, it cannot take on the value 0. It's Q almost surely positive, and it's actually Q almost surely finite also. And P star is actually equivalent to Q in this case. It's not just absolutely continuous with respect to Q, it's equivalent to Q. The next line is actually quite interesting. X star is the only E variable which can be written as the likelihood ratio of Q to some element in the bipolar. Okay, so it really is a generalized likelihood ratio. There's no other dq by dp. There's no other dq by dp that's actually an E variable. There's only one. It's dq by dp star. Okay, and so you cannot write down any other likelihood ratio that's actually an E variable. So this particular one, dq by dp star, is really very special. And finally, P star is also maximal in the sense that it cannot be dominated by any other element of script P of the bipolar that is absolutely continuous with respect to Q, which means that even when it's a sub-probability measure, there's actually no probability measure inside the bipolar that dominates it.
So it's like this is the right generalization of Radhamikidam derivatives to a null class.
Yes, exactly. This is exactly, that's exactly right. This is the right generalization of the Radhamikidam derivative to composite null class with no measurability assumptions whatsoever. Yep, that's exactly right. And it's unique. There's only one way to do it. There's no other way you could have done it. Yeah. Okay, so now some examples. The theory is only as useful as examples that you can now address that you couldn't address before. I love this example. Okay, so symmetric distributions. So I'm going to let Z denote the data in this case. Okay, so so far we have only had, these bets and so on, but let's say we have actual data. In this case, it's real valued. And my null hypothesis is the set of all symmetric distributions. So distributions P in M1 such that Z and minus Z have the same distribution under P. Okay, symmetric. Note that P has no dominating reference measure. You have discrete and continuous distributions with unbounded supports with anything in there. So this is a super non-parametric class. There is no common reference measure. You cannot define likelihood ratios on this class. Okay, so it feels like how would you even start to define a reverse information projection? So suppose now that your alternative Q has a Lebesgue density little q. So it has a density. Okay, now I'm going to ask you, does anyone want to guess what the reverse information projection is here? So we can, even though we don't have reference measures, it seems KL cannot even be defined. We can project Q onto script P. Does anyone want to guess what the projection is?
Some sort of mixture.
I was going to symmetrization.
Symmetrization.
Average opposite points.
Average opposite points. It's almost that. Okay, so older theory does not apply, but we can show that P star of Z is the symmetrization of Q. So it's Q of Z plus Q of minus Z by 2. But not just that, indicator times Q of Z is positive. So that's the part where it's not just the symmetrization, because if you had taken just the symmetrization, it's actually not absolutely continuous with respect to Q. Now I have mass elsewhere potentially, but if I put the indicator of Q of Z being positive, now it's absolutely continuous with respect to Q. That's actually provably the Ripper density. Now I want us to think about this for a moment. This is really a weird object. This is not a distribution unless it's a probability density only if Q has symmetric support, which means this indicator kind of maybe doesn't matter. But if the indicator matters, then it's not a probability density. Now let's take an extreme example. Let's say that Q is one-sided, like it's like some exponential distribution or something of that kind, something one-sided. Okay. In that case, Q of minus Z is 0. Whenever Z is positive, Q of minus Z is 0. And the reverse information projection is Q over 2. Okay, that's the reverse information projection. Q over 2 is not a probability density. You can show it lies in the bipolar because there's, yeah, anyway, you can prove it lies in the bipolar, but it's just Q over 2. That is the reverse information projection. The KL is well defined between Q and Q over 2. And it turns out in that particular case, the optimal bet is just C 0 over 2. So if you see a positive number, it's 2. And if you see a negative number, it's 0 or something. It's just like it's just a simple bet. And under the null, that's equally likely to be it has mean 1. But on the alternative, you get 2 if it's a positive number and 0 if it's negative. It's impossible it's a negative number. So it's like a very interesting and simple case, but it shows you how with this new theory, you can handle interesting non-parametric examples. And then the Numeraire has that particular form. So it's the likelihood ratio of Q to their average. Yeah.
So, what if script P is just a finite collection of symmetric distributions? What would be the projection?
I don't know. Yeah, I'm not sure. Good question. But you'll see some more examples here, including a variant of one where there's 2 symmetric distributions. I'll get to it soon.
If you have a finite collection of measures, you parameterize the weights of combination.
Yes, and then you can solve a convex program.
Solve the expected log.
That's right.
Mixture thing is the log concave maximization.
That's right. Yeah, it's
Have a closed form.
it's not closed form in that case. Yeah, you would have to solve an optimization problem to get it. That's right.
I probably missed something fundamental here.
Yeah.
So this PSAR is not even feasible. So
It's not in script P. It's in the bipolar of P. That's what I'm trying to say. Is bipolar is a larger element.
Is over P.
Sorry.
Isn't reverse info projection?
No. So if I go back to Jonathan Lee's thesis,
General sense.
as Jonathan Lee's thesis says over here, like this. Okay. So anyway, so Q star, you just need this condition for Q star to exist. It achieves the infimum, and of course, the thing that achieves the infimum is typically not in the set, and so on. So yeah, I mean, it's like, I mean, if you think about it, like this was already known that Q star would be a sub-probability distribution in general. I mean, the fact that it's a sub-probability distribution was already in Jonathan Lee's thesis. And so this is just not avoidable. Like even if you add assumptions, lots of assumptions, measures, convey, whatever, you want what you want, the reverse information projection is not a probability distribution in general. The infimum is not in general achieved by something in the set. Okay, so that's symmetric. Let's look at another so in the paper, we actually, the last line here just says, there's nothing that is important about having a Lebesgue density for a general Q, we give it in the paper. Okay, sub-Gaussian distributions. Okay, so let's look at P, which measures such that hopefully people know what the sub-Gaussian conditions is. This is a one-sided sub-Gaussian condition. So for lambda positive, this MGF condition holds. This basically implies that the mean of these distributions in script P is less than or equal to 0. So it's one sub-Gaussian and negative mean. Now I'm letting the alternative be normal mu1. Okay, so for anybody who knows sub-Gaussian distributions, again, it consists of discrete and continuous distributions with any support. There is no reference measure for this class. Can't seem to do KL divergence then likelihood ratios. But does anyone want to guess if Q is normal mu1 for some mu greater than 0, what is the reverse information projection?
Normal 0.
Normal 0, 1, exactly. So it just turns out that there's no reference measure, but we can show that normal 0, 1 is the reverse information projection, and then their likelihood ratio, which is that's likelihood ratio of 2 Gaussians, is the Numeraire. You can prove that. So here's the third parametric example from Lardy et al. That paper. Nice one. So let's say P is just 2 distributions. It's like close to what John asked. Normal -1, 1 and normal 1, 1. Okay, so it's 2 distributions. And Q is a centered Cauchy distribution. Okay, 2 Gaussians is the null, Cauchy is the alternative. So the thing to note, which is interesting, is here the KL divergence between Q and PI is infinity because Cauchy has exponentially heavier tails than a Gaussian. So the KL divergences are infinite. So can you still do something? Yes, you can prove that the reverse information projection is just P1 plus P2 by 2. That's the Ripper, and the Numeraire that's the optimal bet. Whatever the likelihood ratio of Q to P1 plus P2 by 2. It seems intuitive because you have normal -1, 1 and normal 1, 1, and so Cauchy is centered at 0. So if you want something that's kind of centered, you should take an equal mixture and so on. But the thing is, how do you even define these objects when you have infinities going on? They're well defined. The answer is you go to the Numeraire. The Numeraire is always well defined. You define the Ripper via the Numeraire. That's well defined, and things work out. Okay, so of course, in the paper, we generalize this to Q being any symmetric distribution. There's nothing special about Cauchy, but it's just a smaller null. And then people like exponential families. So here's a simple exponential family example. So suppose you have a one parameter exponential family for simplicity. So here we do have a reference measure mu, and this A of theta is a convex and differentiable function. So hopefully people are familiar with this notation. So let's say that the null is given by some subset of theta, which is closed and has the smallest element theta star. And the alternative is p theta 1 for some theta 1 that's less than theta star. Okay, so we have a smallest element and theta 1 is less than that. Okay, in this case, we can show that p theta star, this boundary element, is the reverse information projection, and the numeraire is just the likelihood ratio of p theta 1 to p theta star. And and Andrew pointed us to this paper by Cesar and Matus, which has an extensive study of the Ripper for exponential families, but it does still assume reference measures and things of that kind. So it doesn't really, we didn't know what more to say about it. But anyway, so here's some examples, parametric, non-parametric, that you can solve, and it's very clean. Here's one slide about going beyond the logarithmic utility. So you might say, suppose I want to maximize the expected utility of x over all e variables under q. So under p, it's a fair bet, but under q, I want to maximize it for some other thing other than log. Okay, so let's consider for now. So in our paper, we consider increasing continuous differentiable bounded utility functions. So for example, if you take powers rather than log, that's one example. So we can show that in this case, it's still the case that an optimal bet still exists. It's still unique under no assumptions on script p and q. It still exists and is unique. And there is still a reverse information projection, if you'll call it that. It's a Renyi projection, p star gamma. And so we have a strong duality theorem. For those of you who know Renyi divergence, that's what it looks like. For those of you who don't, it might look confusing, but it's a generalization of KL if you want. And so we show that there's still a strong duality statement that the supremum of this expected utility equals the infimum over P in the bipolar of this Renyi divergence. And it's achieved by this particular pair, which is unique, of this optimal bet and this Renyi projection of Q onto script P. So again, now we can define Renyi projections also again without any continuity, without absolute continuity or reference measures and so on. Okay, so let me just summarize. I'm at time, it's 12:59. So we've fully generalized Kelly betting to composite nulls and point alternatives, yielding a strong duality between X star and P star. We have defined this reverse information projection, P star, and the optimal E variable X star, the numeraire, without any assumptions. We showed how to apply this theory to new non-parametric settings that were previously out of reach. We showed how to generalize this story to general utilities that are continuous, increasing, concave, differentiable, and bounded. And so our next steps are, well, can we handle more general utilities? Answer is yes, but the duality theory gets significantly more subtle. We can generalize this to composite alternatives. This part should be clean. And then generalize it to really sequential settings rather than one round. You have composite alternatives and you have multiple rounds of betting. Now you have interesting strategies. But again, how do you do this without any assumptions and stuff? So we have ideas for all of these, but that's essentially future work. And maybe there's some applications like, can we now do EM because we can do these reverse information projections very generally? Can we do EM in more general settings? Can we handle covariate shift because they involve likelihood ratios, and this is a generalized likelihood ratio without reference measures? So I don't know, other applications there might be. I'm not sure, but. With that, let me just thank all of you for coming, for the great questions, and I'd be happy to stay and answer more questions, but let me stop now. Thank you.
Yeah, maybe you could comment on the relationship to the study of maximum likelihood.
Yeah.
So if you have a parametric family of distributions,
yeah,
but the truth Q
yeah.
doesn't happen to be in that family.
Yeah.
In this story, though, usually we would have a dominating measure.
Yeah.
But then you would say there's a theta star depending upon Q.
Yeah.
That minimizes the pullback divergence from
yes.
Q to that family.
Yes.
Yes. That was the motivation for what Jonathan Lee and
exactly.
I did.
Right. Yes.
Anything to say about estimation, more broadly, because you're allowing non-dominated families?
Yeah, just that the theory would now extend. I mean, yeah, we would not need that assumption, but we would
But
still be
how
able
would
to
we
talk about.
define our estimators if we don't have a dominating measure? What's the analog of maximum likelihood? Something to think.
Yeah, something to think about. Yeah, it's a great question, but I fully agree that yeah, the whole reverse information projections are just intimately connected to maximum likelihood. But yeah, we didn't carefully think about it, but we just said, oh, now we can do it more generally. But maybe we should think about it.
What
more
is
as
maximum
what-
likelihood?
Yeah, what does it mean now? Yeah.
So when you start looking at more general utilities, is there a connection to hypothesis testing?
Yeah, it's still the null is true, but under the alternative, instead of maximizing the expected log wealth, you want to maximize. I mean, it's still a notion of evidence against the null, meaning the larger it is, the more evidence you have against the null. Yeah, it would just be maybe, for example, your risk tolerance when you're actually accumulating evidence against, like the e-variable property still holds, which means under the null you can't make money. But it's like under the alternative, what behavior you want. So for example, if you're more or less risky, you might have other utility functions other than log. I mean, yeah, it's maybe slightly unnatural. Log is the most natural one, but you can do it. So why not? People have often asked why log, and so we said, well, we can do it without log if you really want to. John, yeah.
Okay, follow up with Dan's question. Is there any connection to the generalized ratio test?
Yeah, I'm not sure what connection. So like,
We have the max, then you take the, they think
Yeah.
that wrong is no longer popular anymore, right? You know, and so, I guess there may be some connection with it, no?
yeah, not
I think you're
sure.
on the right track saying Bayes tests, where you would take the alternatives and put a prior on reducing and then to a mixture cube. And then, because that's the Bayes optimal test
Yeah.
in a composite alternative situation, once you have a prior, is a reduction to a simple alternative.
That's right. Yeah. So generalized likelihood ratio is terribly behaved as a test statistic if you don't have a lot of regularity conditions. If you take max under both, you need a lot of regularity conditions to ensure that it has a well-known limiting distribution. Like for example, if you want Wilks theorem to apply, or if you actually want to use it as a test statistic, it's very erratic. But instead, if you a very clean way to derive tests is to work with e-variables, because if you want to reject the null at level alpha, if your e-variable is larger than 1 over alpha, you reject the null. So it's like Markov's inequality suggests that, yeah, thresholding at like if alpha is 0.05, you want level 0.05 test. If your wealth crosses 20, then you can reject at level alpha. But getting a level alpha test for generalized likelihood ratio in irregular testing problems like mixtures, like things with latent variables, like like almost every interesting problem, generalized likelihood ratio is poorly behaved. So you can't actually because under composite nulls, how do you define its threshold and so on is tedious. So I think that yeah, this is just an alternative to generalized likelihood ratio. And I think there's a middle ground actually. So there's something called universal inference, which what you should think of as doing is it's a mixture under the alternatives divided by maximum likelihood under the null. So it's a weird combination of those two. That's always an e-variable. So you can show that if you take soup divided by soup, then that's erratically behaved. If you take mixture divided by mixture, you have no worst case guarantee under the null. But if you take mixture divided by soup, then you have this nice property that it have a worst case type 1 error control under the null, and it's an e-variable, so you can actually run a test and so on under the and it's powerful, and you can show its optimal, things like that. And so you can show that mixture, that intermediate thing is called universal inference, and so it gets around all these irregular problems and so on. You can do irregular inference with universal inference, and you can show that this always dominates universal inference. So universal inference is always inadmissible, meaning that this always dominates universal. It's always a better idea than universal inference. But the challenge, of course, is computing the reverse information projection in particular example. So in universal inference, the denominator is maximum likelihood under the null. We often know how to do that. But here we have to project some kind of alternative or mixture of alternatives onto the null. That may be tricky in particular situations. And so I would say, practically speaking, they're on an equal footing. There's some problems for which universal inference applies. So like if you want to test log concave distributions, your null hypothesis is your distribution is log concave. The only way I know how to do it is via universal inference. if you want to test something like symmetry or something of that kind, then this approach is clean. So right now, practically, you can't even do universal inference if you don't have likelihood ratios. So yeah, so there is a nice story connecting all of these, like full Bayes, full frequentist, which is soup divided by soup, and the game theoretic approach, which I think of as being an intermediate between Bayesian and frequentist. The guarantees are frequentist, but there's a Bayesian way of thinking about it. The idea is that somehow, as a gambler, your optimal strategy is always Bayesian. If you have some prior knowledge, you should use it, and your optimal gambling strategies are Bayesian. But for an observer, the evidence is there. If you've made wealth by betting against the null, I don't need to know or care what your priors are. If you made a lot of wealth, the null is false. So somehow it's objective for an observer, but it's subjective for the actor. So it really finds a middle ground between Bayesian and frequentist methodologies and interpretations. But yeah, maybe more for our meeting. Yeah.
Just a little question. So I like your story. I'm starting with Kelly and into the hypothesis testing. So you get away from communication here. I'm just wondering if you think about codes, right?
Yeah.
Random codes, maybe cheating capacity. Does that have an interpretation in the testing scenario, in the testing view of all of this?
Yeah, I guess maybe this property is the one that maybe I referred to. It's like this description game thing. If the data is actually coming according to Q, then maybe coding according to P star is a better idea than coding according to any other P in the alternative. You cannot gain in description length by switching to some other P. Maybe that's one connection of all of this. Like the reverse information projection gives you some kind of optimality theory with respect to coding. But other than that, I have not carefully thought about if I was actually doing communicate, like what this really means for communication theory. It's just there is an interpretation of all of this in terms of description game, but I don't know if maybe Andrew finds it easier. I don't think really in terms of communication theory very much. So
Well, thank you very much again.
thank you.
So Aaditya's schedule, so for like the next 20 minutes, we just have like break labeled, so I don't know, grab more food, grab coffee, meet in the common room, ask more questions. And the whole in your schedule is at 2 o'clock.
Okay.
So either Andrew runs for a long meeting or.
So if someone speaks up, come and grab them from me.
Okay, that's a good thought, right? So if you want to grab them at 2, he'll be in Andrew's office.
Right.
So I was wondering for the strong graduate result, what if we just extend it to general divergence? Does this still hold?
That requires extending our theory to unbounded utilities. So we did only Rennie so far because it's still a bounded utility function, but
Here it seems your utility is small, it's also unbounded.
yeah, so it works out for, so there's like very special duality theories that work for log and then work for bound utilities. We know how to do it for general utilities, but it'll require much more work. The reason is that, like I'll give you a rough intuition where the challenge lies, is that usual duality theory works in vector spaces. So, but the set of positive random variables or the set of positive measures they're not vector spaces because differences take you outside the set. So, usual bipolar theorems do not apply, but we used it in the Annals of Mathematics in 1999. There was a paper by Warner Brannett and Schaffermeyer that derives a special bipolar theorem for these classes, for non-negative measures.